Now let's look at our next function, which is the factorial function. Now we have covered this before in previous videos over the last 2 courses, so some of this will be revision. Now we're going to take the recursive algorithm that we generated at the end of the second Design a CPU course for the factorial, and we're going to take that recursive algorithm and we're going to update it and create it as a subroutine inside the ROM. Now the factorial is written n with the exclamation mark, and we just read this as n factorial. N factorial is just a multiplication of the descending numbers. So if we were to write 5 factorial, it's 5 times 4 times 3 times 2 times 1, which is 120. Now the value of 0 factorial is defined as a value of 1. The option of having negative numbers isn't available to us. So minus n factorial doesn't exist. It is the empty set. So we want to build this little function into a subroutine in the ROM. So let's go do that now. We are going to have the 2 pieces of code here. The one on the right is the calling function, the one on the left is the subroutine. So let's work through the calling function first of all. In order to work out our factorial, we only need one number. So we'll call this number n. Now we're going to push n onto the stack, and then we're going to jump to the subroutine math underscore factorial. Now the position for math factorial is 0 cross 1090. So this is the start of the subroutine within the ROM. And again, I have chosen this using the spreadsheet, which gives us the memory locations within our ROM. So at that point, we're going to jump to the subroutine math underscore factorial. So at that point, we jump in here to this address 0 cross 1090. Now we then run through the factorial, which we will talk over in just a moment. But when we get to the end of the factorial, it returns a result. So it puts that result into memory. And then what we do here is we grab that result from memory and we stick it in register R5 just for convenience, so we can see the actual code working. And then the program ends. So that's us talked through the calling function. Let's go into the subroutine. So let's talk through the factorial subroutine. Now, you have seen this recursive subroutine before in Design a CPU 2, and there's a video there called Recursion. So if you get stuck at this video, you can always go back to the second course and check that video out, and we work through that recursive algorithm in detail. So let's talk our way through this now. We're going to first store the register values that will be overwritten within the algorithm. So we're going to store the index register here, the register R0 and register R1 in these temporary locations. We're then going to pop off the return address, and we're going to pop the value n into the index register. Now the first part of this here is our housekeeping. So first of all, we want to check and make sure that we don't have any values of n which are negative. So we compare the index register with 0, and we jump if a is greater than to the trap a. So that's really saying that if this number here, 0, is greater than the index register, the value in the index register, then the value in the index register must be negative. So in that case we jump to the trap A. So this is us jumping down here to the trap, and we can call this trap number 4, and we save this value in the memory location called trap. And again, the trap memory location is a fixed defined address where we put all of our trap error codes, and it's 0x E7F0. Now, another thing we do here is whenever we put that value into the trap address, straight after it, we still restore the values for our registers, the index register, the R0 and the R1, so they go back to what they were previously. And then we jump to the return address, and the return address takes us back to the calling function. So that's for negative values, and we know those don't occur, so we have this trap here to test and see whether that has happened. So the next thing that we're interested in the housekeeping is whether the value is 0. 0 factorial is defined as a value of 1. So we jump if it's equal. So if the index register contains a 0, we jump to the 0 section here. At that point here, we come down and we put the value of 1 into register R1, which will be a final output, and we store that R1 in result, and again we jump to end. So the end section here again restores the registers and then jumps to the calling function. So that's us covered the housekeeping section. Let's move on to the recursive algorithm. Now, if the value for n isn't negative and it isn't 0, then we have to work out the factorial. So at that point here, we jump down to this line, so it jumps to subroutine factorial. So we jump to this point here. Now at this point here, we're going to push the value of n onto the stack again, and we're going to subtract the value of 1 from it, and then we make a comparison to see whether the value for the n has gone to 0. Now, if it hasn't gone to 0, then we jump to subroutine factorial again. So we come from here and we jump back up to this point, and again we push the next value for the n onto the stack and then decrement, and we keep doing this. So if we keep working through this little bit of the loop, then what it does is it puts, for example, the value of a return address, then the number 5, return address 4, return address 3, return address 2, return address 1. So all these values will be put onto the stack. Now whenever the value for n goes to 0, that means we've got all the return addresses and all of the values on the stack. So at that point here, we jump to the out, so we jump back down to here. So now we're going to actually go through the multiplication. So we pop the value of the stack into register R1, so it's going to contain the first number, for example 1, and then we come up and we jump to the return, so we return here, and when we return up to this line here, and then it's going to pop the next value off onto register R0. Now the next value it pops off isn't a return address, because it shifts up 1 above the return address, because this return here will change the position of the stack pointer. So now we've got the next value in the register R0, so we multiply the 2 times the 1 and we put the answer 2 in register R1. So we've now got the number 2 in register R1, and we come down and we jump to the return again. So we jump back down here and we return back up to this point, and we take the next value out, so we're going to have the value of 3 in register R0 and 2 in register R1. So we multiply them together, 3 times 2 is 6, and we keep going through this process until eventually the very last value that we do the return from will actually return back up to the original factorial point up here, so it'll jump up to the next line up here. And the value of R1 will contain the result, and we place that in result, and then we jump to the end. We get to the end here, and again we restore the values into the registers, and we then jump to the calling function. So it's a difficult process to describe. I have already described this, and I've shown it, as I said before, in a video called Recursion in the second course. So if you're still stuck at this, then I suggest you go and have a look at that video. You can run the simulation from that video, and you can also run the simulation from this video as well. And from running the simulations, you get a better idea of how this recursion process works. So I do suggest that you go ahead and do that. All of the files will be in the resources section, so you can download and recreate everything for yourself. So let's quickly see this working. We won't go through it in all detail, but we'll just see a couple of values running through, and we'll see it actually operating. Now let's go through just 2 examples. We will go through the example of using a negative number. So we can put in -5, and we'll save this, and we will assemble it. Now it's been assembled here, we can load up the code into our RAM. And we will run through the simulation. So this should give us a trap, because we can't put in a negative number. There is no such thing as a factorial of a negative n. So you can see the trap light has come on, and it's given us a trap error of 4. Again, we could go to a spreadsheet, and then we could look and find trap error 4, and then we would know the trap error 4 would tell us that we have tried to put in a negative number in for a factorial. So let's go through, and we'll stop this just now, and we'll go through one more example. So in this example, we'll just put in another number. So we'll put in the number 5, and again we will assemble it, and we get the code out here, and we'll load up the code onto our machine. And then we can run through this. Now, whenever we run through this, we will be generating we were putting the numbers into the stack, so it will be the number 5, and then the return address 4, return address 3, return address, and then we'll start multiplying 1 times 2 times 3 times 4 times 5 in registers R0 and R1. So you'll see this actually happening. So this is the first part of it here, where the index register is going to count down from 5, 4, 3, 2, 1, and then we start the multiplication here in register R0 and R1, and you can see these multiplications happening. Now we finally put the result, which is 120. Now 120 in hex is 78, so we've got the result in register R5, and we have restored the original values for registers R0 and R1 to the value of 0. So I'll stop this from running, and that's us work through our factorial function. So in the next video we will go on to another mathematical function. So thank you for listening. I'll get you on the next video. Goodbye.